Here we are. Okay, so let's start, guys. Welcome to the first live session in which we're gonna do something more than just talking. So we're gonna show some code, we're gonna try to run some code, and at the end of the day, I wanna show you the workflow, the thought process, the steps that at least I follow, and I think makes sense to follow, to fine-tune a vision language model to a particular task. In this case, a task that I picked is a car marker identification. So this is essentially a classification problem, which is not a trivial problem because this is not distinguishing between cats and dogs. It's a little bit more involved. So you will see that during the whole exercise, we will need to be careful, okay? So fine-tuning language models, fine-tuning especially small language models has a lot of upside, like it's super cheap once you have the model running, it's super easy to deploy, it's super cost-effective, you can deploy it in many other places, meaning you don't need powerful GPUs, but on the con side, it requires a little bit of care and love initially to build that model. So going from, hey, I have a data set, and hey, I want to build a model that is good at this data set, to the point where you have the model that works well for that specific task, it takes a little bit of experimentation, a little bit of back and forth, and this is precisely the kind of process that I want to be super honest with you. I want to show you step by step for this example, so you can hopefully extract some learnings, feel better prepared for the next time you want to fine-tune something for your particular use case, okay? So these slides are amazing. By the way, can you see the slides? Benito, you are not the shy guy. Can you see them?
Yes, I can see the slide.
Super. So I initially said, let's fine-tune LFN2BL to identify car makers, but then I realized that fine-tuning is just part of this whole process that I'm going to show you today, okay? So actually what we want to do is we want to build a model that is good for this task. What will happen is that, well, the first 2, 3, 4 things we will try will improve our model, will give us some, let's call it baseline performance, which is not going to be good enough. So we will need to take one step further and cover fine-tuning. And obviously, we're going to take this one step further and do the fine-tuning, because otherwise, I wouldn't have named this session, Let's Fine-Tune a Vision Model. So in a nutshell, what are we trying to accomplish here? The idea is super simple. We're going to take, we want to build a program. Computer program is essentially a machine language model, in this case, a vision language model, to where you can present an image of a car and you can ask a very simple question, which is, what car maker do you see in the picture? And we want our model to provide the correct answer, which in this particular case, for example, is Audi. How do you know it's Audi? Well, because we human beings, along our, 20, 30, 40 years around living on this planet Earth, we have learned that Audi as a brand has this very distinctive symbol consisting of 4 circles. So when you see this car, you focus your eyes on this kind of the part where there's the Audi symbol, the 4 circles, and they say, this is an Audi. So the question is, how can we build a computer program that is able to follow maybe a different procedure, get to the same conclusion, which is this is Audi. This is, in a nutshell, what we're trying to do here. So going step by step, what will we cover today? So as you can see, I prepared this thing really quickly here, but the main takeaways here, the kind of techniques that I want you to learn that transfer to any other problem you want to solve are, first of all, structured output generation. What is that? We're asking a language model to output not any kind of text, but text with a very specific format. In this case, the word, the text that this language model, that this vision language model outputs needs to be the name of a car maker. So, which means it can be Audi, it can be Tesla, it can be Mercedes, but it cannot be Pau, because as far as I know, there's not a car maker in this world named Pau. Yeah, Okay, so there are some restrictions regarding the output this model needs to produce. And the question is, how can you ensure your language model generates this kind of structured output? So this is the first thing we're going to see today. Once we have this thing in place, or actually before that, I'm going to show you the first thing you need to build in any project, which is your evaluation loop. What is that? You have a task, which is identify car makers from pictures. You need to find out if model A, B, or C, how good they are at this task. You need to evaluate them. And the key element is you construct, you build, we're going to see soon, an evaluation script, I call it loop, that is model agnostic, meaning it's in general a Python script where you can plug different models with different configuration parameters, and you don't need to change the business logic. You run it and you get a number, which is the evaluation metric. And this measures how good model A is for this given task. And this way, basically, you can rank different models and you can track progress. Because sometimes, as you will see, you fine-tune a model and you produce a model that is actually worse than the original base model you started with. Okay, so super important evaluation loop. Without that, you are driving blind. So we are going to cover that. Now, once we're done with structure generation and evaluation loop and basically doing some tricks, we will see that our models are not really good enough to be called production ready. And this is when we're going to enter the fine-tuning. And fine-tuning, as I said, it's a process that requires a little bit of care and love. Some of the things that maybe you haven't encountered before doing machine learning work that you need to do well here, otherwise you're screwed, are first of all, you need GPUs. There is no way you can fine-tune models, even small ones, without access to GPUs. And unfortunately, or I don't know how to call it, most people in this world do not have a GPU at home. So you need to find a cost-effective way to get the GPU, to set up the right environment inside the GPU, to run your fine-tuning script, and then shut down. So I'm going to show you how you can get on-demand GPUs in a cost-effective way. Then I'm going to show you how to keep this whole code that we are going to see pretty soon organized, meaning there's a lot, especially during fine-tuning, there's a lot of hyperparameters. There are a lot of things, a lot of parameters regarding the model, the dataset, the LoRA. We're going to see what that is regarding how you do the fine-tuning. So there are a lot of parameters you need to fix, and then you run your experiment. And there are so many, and you are not sure which ones work best, and you're constantly experimenting. So you need to separate configuration from code. And this is super important. You're going to see it in a couple of minutes. Third element, which is super important related to this, we're going to run a lot of experiments. So you need to use the proper tooling to track the result of each experiment. And here I'm going to use weights and biases. There are other experiment trackers, for example, MLflow, for example, Comet. There's also Neptune. I'm going to use weights and biases because it's the one that I'm using lately. I mean, it's quite good, honestly, so let's use it. And it integrates really well with other Python libraries. And then fourth element, which is super important, which again transfers to any other fine-tuning you're going to do from now on, which is error analysis. Super important when you fine-tune a model and you get a model that you perform this kind of dissecting. Where is the model good at? And especially, where is the model bad at? This is called error analysis. This is something that if you come from traditional machine learning, if you have, for example, participated in Kaggle competitions, this is the kind of, okay, post-mortem of a model, right? You take the model, you generate predictions of the test set, you compare with the actual ground truth, and then you start discovering where is the model failing, and maybe you get a hint of, okay, if the model is, for example, consistently bad at predicting that this is a car maker Ford, so it's, for example, mixing Ford with Chevrolet, maybe this tells you that, okay, maybe there's a problem in the data, a data labeling problem, or maybe there are not enough samples, and you can basically generate more samples of Ford cars and Chevrolet cars, and by providing more examples, you help the model draw basically the frontier between these two classes better and perform and be more accurate in its predictions. Okay, so 4 elements we're going to cover, and one key learning, which, I mean, we're gonna see what that one key learning is. And then, as I said, this is work in progress. I started working on this thing a few days ago. I haven't managed to solve it perfectly. So I haven't managed to build a car maker classifier that works 99% right, which is what I want to build. So I'm going to leave some challenges that I'm going to work on my own in the following days, but I dare you to try them, okay? Because this is the only way you learn, okay? You won't learn by watching me today. You will just learn trying to solve challenges yourself. So you're going to have challenges. And before we start, all the code that I'm showing, it's under the Liquid for All cookbook repository. It's not under the main branch. It's called under a feature branch called POW, Car Maker Identification. So feel free to go to the repo. You can git pull the code, git checkout to this branch, and you will see the exact same code that I'm going to show you and use now in this session. Okay? And that's it for slides. Let's go with the code. Okay. So here's the car maker identification. And here I prepared some bullet points to guide me with this presentation. So what is the vision language model? We covered that, right? It's a language model that accepts 2 kinds of inputs, text and image, and produces an output which is text. They're useful for basically image understanding, image captioning, image segmentation, image classification. This is the task we're going to solve here. So first one, good job, Pau. That was easy, huh? By the way, if you have questions, please, I'm gonna go there. Go on Discord and you share them on the channel. So let me go there. Oh, come on. Oh boy, let me go to another Discord. So anyway, you know the channel. Oh, here it is. Here it is. Oh, I love it. Here it is. So all the questions you have, please go to live events. All the questions for the live event. Go for the live for today's live session. Go here, please. Everyone. Okay, so send now, and then I'm going to start the first. So create a thread. What's my name? My name is Pau. Okay, so that's the first question. You have here the pointer. Okay, so please dump your questions there, because if you ask here on Zoom, I'm going to lose them. So second element, dataset and task. You know the task, let me show you the dataset. So the dataset, let's go to Hugging Face. So Hugging Face, let me go there. It's under my profile. Here it is. Okay, so there's a dataset called Stand for Cars. I did not create this dataset. This dataset is the standard stand for cars. You can find it on Kaggle. Basically, I got it from another GitHub, from another Hugging Face dataset. And what I did is I extracted the images, and then I extracted the car maker. Okay, this is the string we want to predict. And as you can see, it has up to 49 possible values. For example, it has Chevrolet, it has Dodge, it has Audi, it has Ford, BMW, etc. It has up to 49 classes, and they're not all equally represented. So, for example, Chevrolet has 11.6% of the samples are Chevrolet, then Dodge 7%, 7.7%. And then as you go down, for example, there are cars like Rolls-Royce, which has only 1.4%. So what I'm trying to say here is not a perfectly balanced data set. And why am I saying this? Because, as usual, if some classes are underrepresented, for example, Rolls-Royce, it's harder for the model to, in general, to distinguish them well, to classify them well. Okay, and these details are important. So the data set is here. 2 important observations. The key learning from today. A fine-tuned model is as good as the data set you use to fine-tune it. Meaning, the key, the secret sauce of a good fine-tune is not about the LoRA parameters, is not about hyperparameters here, it's not about the learning rate. Yes, they matter. But the first thing, the deal, what makes or breaks the deal here is the quality of the data set. And what does quality mean? It means two super important properties. It means the data set needs to have accurate labels, meaning if this picture is a Volkswagen, but the data set has a wrong label and says BMW, this is a problem of data quality. You need to identify and fix that. This is something that I haven't done here. Okay, so I took this data set and I did not perform any kind of verification of labels. It's a bit weird that I'm going to advise you to do that when I haven't done it, but I didn't have time here, okay? I wanted to get fast results. But in general, data quality is something you need to double check. What people do in practice, which is what I've done here, is you take this data set as it is, you start the fine tuning, and then once you get the results and do the error analysis that I was talking about before, then when you see that the model cannot learn well certain classes, now you go back to the data set and, for example, check data quality issues like what I've just said, wrong label. So first important property of a good data set, it needs to be accurate. And second super important property, it needs to be diverse enough. What does it mean? If this data set that we're using here contains 49 classes, but as we know, probably outside in this world, you can go to the streets and find other car makers which are not represented here. If you fine-tune a model on these 49 classes, but now you deploy it, let's say you deploy it on a self-driving car, and the self-driving car sees a car that does not belong to any of these 49 classes, your model will just not work. Okay, so the fine-tune will look amazing on your own evaluation data set, but in production, it will fail. And this is why it's important for a good data set to be diverse enough. You want to cover the whole distribution of inputs that your model will see once deployed in production. Okay, this is not something specific to language models. This is a property or a weakness of machine learning models in general, which is they're very fragile. They are not able to learn things they haven't actually seen before, especially when we're dealing with classifiers. If there are classes that are not represented in your data set, they're not represented enough in your data set, like for example, Rolls-Royce, the model will have a hard time predicting this is a Rolls-Royce. Okay, these are two things that I haven't covered on this data set, but these are things that as soon as I get some time, I want to get deeper on that. And probably we're going to have a session just on that, on how you effectively increase the quality and the quantity of your data set. Super important. This is essential for fine-tuning. We are not going to cover it in depth today, but I want you to be super aware. When you are trying fine-tunes for days, weeks, and you're desperate and it doesn't work, my advice, go back to the data and check the data. And more often than not, you will be surprised how many errors and how many underrepresented classes examples are in your data set. These are the things that if you fix them and you fine-tune again, you will improve your results. So, second element, data set and task. X. Bravo, Pau. Okay. I think I deserve a coffee. Third element, super important, GPUs. I'm using, for example, a MacBook. I have access to GPU. It's not an NVIDIA. It's not based on CUDA. It's based on Metal. But still, it's not ideal. Why? Because traditionally, deep learning libraries, in particular PyTorch, were built for, as almost anything, were built for NVIDIA GPU CUDA drivers. Okay, so there are lots of things that they don't really work well when you don't have that kind of GPU. Moreover, if you don't have a GPU to start with, then you are completely, how should I put it, screwed. Okay, you need a GPU, but GPUs are expensive. So the question is, how can you get a GPU without the bank? Okay, and this is something that this is my personal choice. what I do, there are several options. There are people who go to services like, for example, RunPod. You can go to RunPod. You can go and you can rent a GPU. You can go. I think you can go to Vast AI. I think you can rent a GPU. What I prefer is, instead of allocating and renting a GPU for N days, there's another service which is called Modal. Here it is, modal.com, which offers you access to GPUs without having to provision any infrastructure yourself, meaning there's no need to create Docker files, there's no need to push Docker images, you don't need to run containers yourself. So it's this kind of cloud environment where you can push your Python scripts and say, hey, I want you to run this script on that kind of GPU, run it for me. And it's super easy, and you will see it very quickly. Okay, so my advice, by the way, I don't work for Modal. They don't pay me any money. I'm not sponsored. This is what, as an engineer, if I need to get access to GPUs, which for fine-tuning I really need, this is, in my opinion, the easiest way. And it's actually, they give you, I think, $30 per month. You can see here my score. I have more because I paid $10 a couple of weeks ago. You can run a lot of experiments. So I've been running hundreds of experiments in the last month, and I think I spent like $10. Like, I ran a lot of experiments. So here's my advice. Here I have the GPU, and these are another ticks, another box that I tick. Okay. Now, let's now enter into the code. As I said, it's under the cookbook, under examples, car maker identification. It's under this branch, not a main, because I want to finish before I commit it to the main branch. Now, when you dip into the code, okay, so how did I create this thing? Now it's created, so let me show you. I'm here on the car maker identification. First thing, I'm using UV. If you don't know what UV is, it's probably because you've been living in Mars. Okay, so UV by Astral is a tool that really simplifies how to bootstrap and how to package, especially Python projects. So it's a tool that helps you create virtual environment and manage dependencies super easy. And it also works super fast. So at the moment, it's like, it's a no-brainer. I used to use Poetry for years. This is the second choice here. But when UV came in, it's actually way better. Okay, so, and as it's shown here, faster. So to bootstrap this project, basically I did something like UV, init, yes, car maker identification, and then --lib. When you use --lib, basically you package your code as if it was a Python library. I personally prefer that. I prefer to build everything as a package, because then all the imports, you solve all the problems with imports. Okay, it's super easy to solve those issues. This is the command that I ran to generate the boilerplate. Now, when it comes to the code, it's under the source folder. So let's first go to the evaluation, which is implemented inside evaluate.py. Okay, here we are. What is this thing doing? If you scroll up, I've been playing structure output. Yeah, I think I'm fine. Okay, let me just check if there are some changes. Let me check git status. Okay, it's fine. These are the changes. So what is this file? Let me check the entry point. How do you, first of all, how do we run this script? Let me see. To run this script, and this is something that I personally always do, I create a make file which contains the main commands that I'm constantly running. So I don't need to remember long commands because I don't like that. I like to, for example, create a command to evaluate. I call it evaluate, and this is what it does. So it does UV run Modal. So Modal is a package, a Python package that you install. So in the Py project, you will see that Modal is there. So to install it as any other Python package using UV, you can do clear, you can do UV add Modal, and it's there. Okay, now it's already installed, so nothing to do here. So once you run Modal, you install Modal, you can do things like UV run, and you run the tool. And obviously, it's going to just print some messages. So this is the Modal CLI. Okay, so let me go back to the make file. UV run Modal run. So the Modal run command runs a Python script using the Modal CLI. And what am I running? So I'm running the module, which is located under source car maker identification evaluate. And then I'm passing a parameter, which I call it the config file name. Let's go step by step. If you go to this file, to the evaluate, which is what I have here, if you scroll down, you will see that there's a function which is decorated with the app.local entry point. What is app? If you scroll up, you'll see that app is a Modal application. So here, this is a utility function that I created here in Modal Infra that does get Modal app that returns this Modal app object. So this is the most fundamental element when you use the Modal SDK, the concept of an app. Okay, if you go to your dashboard, to your Modal dashboard, let me go there. You will see your apps are here. Okay, so in this case, there is no live app. As soon as I run the evaluation, you will see the app showing up here. Under which name? Under the name, let me go here, car maker identification. Okay, so let me go down to the entry point. With the local entry point, what I'm saying is when I run this evaluate.py script using uv run modal run path to the script, this is the function that I want you to execute. And this is the parameter that I expect you to pass from the command line. So if you observe here, this name, let me split screen, is the exact same name that I'm passing here in the make file. So let me put it here. In my make file, if you observe, I'm passing this parameter config file name, which has the exact same name, just replacing this scores with underscore, but it matches the parameter I have here. So this is the way to establish the entry point your script when you do modal run. And what it means is that first it loads the configuration, and then it launches. So it launches blah, blah, blah. It launches another function under remote. So what is evaluate? Evaluate is another function that I have here, which has this, it is another modal decorator. In this case, it's not app.local entry point, but app.function. And this is super important. App.local entry point, which is what I've seen, runs on your computer. It runs on Mac here or on Windows. If you're using Windows, it runs on your machine. But as soon as you call a function, in this case, evaluate.remote, and the function is decorated with this kind of information, you're saying, hey, Modal, when you run this Python code, I don't want you to run it on my computer because, look, I'm going to do some heavy computing. I really need a GPU. Please run it on a GPU with this specification. And also, that's not enough. This is just the hardware. I also need to provide the virtual environment. So the collection of Python dependencies you need to install inside that sandbox in order to run my thing. And obviously, it's not enough. So if you come from a cloud engineering background or you have used Docker, you will know that it is not enough to specify the Python dependencies. There are system level dependencies you need to specify to have a full specification of the box, of the pod, call it however you want, whatever you want, to specify the environment where you run this code. So if you go to this image, you will see that this image, it comes from get docker image, which is right here. So get docker image, this is the nice thing of Modal. You can specify, there's no need now for me to write a Docker file, to push the image, deal with Docker repositories, image registries, sorry. No, you just say, look, I want a base image, which is Debian, so Linux distribution with Python 3.12. And now when it comes to Python dependencies, these are the installs I want you to run. Boom. That's it, okay? So that's the magic of this Modal here. So I set the environment. And then apart from that, when you run code in a virtual environment or even your machine, you need to provide sometimes secrets through environment variables. So this is what I'm providing here. And also volumes. Volumes is a way to attach persistent storage to your function. So in this example, for example, or as we will see later in fine-tuning, when you fine-tune a model, you create a model with the parameters you fit, and you need to save that model somewhere where when the fine-tuning is done, you don't lose that, okay? So you need to persist, and volumes are exactly for that. So if you go to Modal, you also see that there's a part with storage. So these are actually the volumes, okay? So volumes are used for persistence. Apps are compute runtime. Storage are volumes. So volumes are storage, the place where you store artifacts, models, model weights, especially in this case, okay? So what's inside evaluate? Okay, here I'm just gonna guide you through the main steps, but basically you load the data. You can inspect the function yourself. This is not rocket science. You will understand easily. So we load the data set from Hugging Face. Then we load the model and processor from Hugging Face. One piece of advice, at the moment, this thing is not caching things. So every time it downloads a model, which is a pain in the arse, and then it starts the proper evaluation loop. What does it do? For every sample, it does what? It extracts the image, it extracts the label, it creates the conversation that you need to pass to the visual language model. And now here there's an if. And this is the first element here, structured output generation. If you decide to do structured output generation, you use this function. We're going to see later. Otherwise, you just create the model output. So you check the result. If predicted class matches the label, accurate predictions +1, otherwise +0, meaning it doesn't change. And then at the end, when you're done with the loop, you print the accuracy and you return this report. This report is essentially a CSV file that we can save locally here. Okay, so I'm talking a lot. Let's try to run it. Okay, so let me take one of the first configurations. So in general, before fine-tuning, you need to establish baseline performance. And what models can I choose from? Well, here I'm going to try liquid models. I'm going to use LFM2VL models. And there are 3 versions. There's the 450 million parameter, the 1.6 billion, and the 3 billion. And these configurations are specified, for example, here. Okay. So in this case, I'm using the 3B, structure generation false, 100%, blah, blah, blah. So let's actually try to run this thing. So let's do make, evaluate, and then I'm running what config. Let me put it here. I'm doing make evaluate, let's say I'm going to do v0.yaml. So let's see. In this case, I'm kicking off the evaluation loop using all these parameters. So I'm going to use the 3B model without structure generation, meaning how is this thing going? 2 very important parameters in your config are the system prom and the user prom, especially the user prom. These are the instructions you send to the model to say, hey, please, this is the question I'm asking you. This is your reference, okay? This is how you should generate your output, the instruction. In this case, I'm saying, what car maker do you see in this picture? Pick one from the following list. Now, this is a pretty long prompt. And the thing is that you can ask the question, where did you get this prompt from, right? Because this is not the simplest prompt. A simpler prompt would be, hey, what car maker do you see in this picture? That's it. And then you are actually asking the model to guess the car maker. And we can actually test that. We're gonna I don't think I have time, so let me check the. You know what? Let's do it. Let's do 3 versions because I want you to see how do the results change. I think it's going to be a good exercise. So let me create 2 configurations. You know what I'm going to do? Look at this. I'm going to leave this thing so in case it runs. And then I'm going to do the thing. The first version is like, hey, I'm not going to provide you with the list of brands. I'm just going to say a very simple prompt. And why am I doing this? What's the takeaway here? The takeaway is that when you want a model to perform good at tasks that require really structured outputs like classification, you need to be careful starting with the prompts, okay? So you can see this thing is running, which is great, super. So you can see we're going to run an evaluation of 100 samples. This is the number here, okay? This is why this progress bar here has 100 as a maximum. And we're going to compare against the ground truth. So we're going to see how accurate is the LFM2VL3B out of the box, meaning there is no fine-tuning here. And you can see that the accuracy is actually 66%, which, look, it's not that bad. There are 49 classes to predict from. To give you a sense of that, I created a notebook that you can run. So let me see if I'm running it. Yeah, here it is. So let me actually stop. So under notebooks, you will find a notebook called Visualize Evals. And I created this notebook to basically understand the result of an evaluation. So you do make report. Let me go there. it's going to start a notebook where if you run it, what this thing is running, let me do it like this. It's going to take the last. So every time an evaluation run is finishes, let me go to the script, I save a CSV file. So every time this thing is done, look at this, I create a report, and this report is saved to CSV. This CSV file goes to this folder called evals, okay? And this Jupyter notebook that I'm showing you, what it does is it goes to the evals folder, and when you use the from last CSV, it loads the latest CSV, in this case, the one that I just generated. And it does what? It does two things. It first prints the confusion matrix, which is a matrix that compares actual versus predicted labels. And then also it allows you to go individually into specific examples that were misclassified. So it gives you both the overall kind of metrics and also the sample by sample analysis. There are other ways you can perform this analysis. There are more sophisticated tools to perform this kind of analysis, like for example, OPIC. I can show it here. OPIC by Comet, it's here. But look, sometimes it's enough just to build a minimum Jupyter notebook or a minimum web app to perform this kind of forensic stuff, okay? So if you run this thing here, let me run it. We're going to see how accurate is this model out of the box. So look at this, look at this horrible matrix. Let me check the accuracy, yes, 66, okay? So look at this. This matrix is horrible. And what's happening here? If I dig deeper, you can see that the model, the things that the model predicts are actually, it's okay, but sometimes look at this. The model is outputting, really text, which is not a car brand. Why is this thing happening? It's happening precisely because if you look at the config that we use, which is this one, I said structure generation false, meaning I'm not constraining, I'm not forcing the model to produce a string that belongs to this set of categories, meaning Audi, BMW, Tesla, Ford, etc. So the model is not bad. It gets 66%. So you can see the elements in the diagonal, for example, for Audi, is getting the 13 samples are like spot on. So the model is great at identifying Audi cars, but then obviously it's not perfect and it fails, okay? So this is the first experiment we run. Now, the one that maybe it makes sense to launch is this one where, okay, in this first version, the prompt, there's no structure generation, and the prompt, look at this, it's super simple. I ask you, I'm going to commit this thing and I invite you to run, but my intuition is that the accuracy we're going to get here is going to be even lower. So 66%, I guess here you can get maybe 40%, which is not bad, but still, this is not something you can really deploy in production, okay? So now the third iteration, big change, structure generation, let me set it to true. Okay, so I'm going to say, look, I'm going to force the model output to belong to these classes. Before we run, or while I run, so we don't lose time, I'm going to explain how does it work. So let me go here, let me clear, let me run this experiment. So make evaluate, it's the V2. Let me run it. Okay. So while this thing is running, how does structure generation work? So let me show you, because I wrote actually on my newsletter an article on that a few days ago. Let me go there. Post structure generation and how to get JSON. Yeah, here it is. I'm using it because it has nice diagrams, nice charts that I think are quite what's happening. Okay, so this is what I want you to look at. When a language model generates an output, it does that token by token. So every token is actually the result of sampling from a distribution. So the LM, the language model, does not directly produce tokens. The language model at each step generates a probability distribution, which means for every token in your vocabulary, it assigns a probability, saying, hey, I think it's 90% likely that this is the best next token you can use. Now this second token is with 10% probability the second best, and then smaller ones. So it generates a probability distribution. So in general, or in principle, once the language model generates a probability distribution, you can force this distribution to match a format you want. For example, if you want a model to produce output, which is JSON, like in this case, JSON that contains a key called pred class, meaning predicted class, and then either dog or cat, what happens is that in the first, second, third, fourth, fifth, so in the first 5 positions, the output the model needs to produce is deterministic. So it needs to be always the first token this one, the second token this one, the third token this one. So how do you ensure the model generates those tokens? Because otherwise you won't get the valid JSON you need. To do that, you need, as I said, to modify the distribution used for sampling. And to do that in practice, you don't need to implement this thing, right? There's a library called outlines. So outlines by TXT is a really powerful library that helps you exactly do that, get structured outputs from LLMs. And this is the one that I'm using here. So if you go to the code, look at this thing is running, super. If you go to the code under evaluate, you will see that I'm doing here. If you're using structured generation, this is the function, line called here. He gets structured output. Cursor here, not really nice with this thing. Okay. I'm using outlines. So I'm using outlines. To use outlines, it's super simple. I just need to wrap my conversation with this chat object. And now the key here is I create. So outlines model is basically a wrapper around the original model. So just to make it, this is how it works, the outlines library. Then the key thing is that I need to specify an output schema. And the output schema is here. So in this case, I'm doing car identification. It's a car identification problem. I say, look, the predicted class that I want you to output needs to belong to this set of categories, right? And outlines basically ensures that when I sample, I make sure that every token that I sample matches, so I get consistent output. And in a nutshell, look at this. Look at the accuracy. Now the accuracy has jumped from 66 to 81. Still, no fine tuning. The thing that I did here is structured output generation. So the takeaway here is for most problems, most business problems are not about generating free text. They're about generating structured output. If you want your language model, if you want your visual language model to perform well at that task, you need structured output generation. Okay, so if you go to the notebook, you can actually run it. So let me rerun it. Look at this. Let me rerun it. And now it's going to pick the latest CSV file, which is the one that was just generated by this run. If you run this thing, look at this. This confusion matrix is way nicer. And the accuracy, as you can see, is 81%. If you observe here, under these categories, now there's only car maker names. There are no more these basically weird sentences that the language model was generating. So this is the power of structured output generation. And as you can see, the model out of the box is pretty good. Again, Audi is like spot on. Chevrolet is also excellent. And then it has some problems with Ford. Okay, so there are 11 samples for Ford. 7 of them are perfectly classified. 4 of them are off. So look, it's not bad. I mean, we spent 0 time fine-tuning this thing and it works quite well. So out of the box with this model, we get 81%. Now, obviously, I'm picking the 3 billion model. What happens if, for example, the application you're trying to build needs to run on mobile devices? In regular mobile devices, the 3 billion model is probably too large. It does not fit. You would need to pick a smaller one. So the question is, for example, if you take the small one, the 450, how good that model is? Let me actually try. So let me take this eval, this one. Let me copy it. And let me change it for the 450. Because I want to give you here, basically, we can understand what's happening. So the 350 is 450 megabyte, million parameters, sorry, is this one here, stand for cars, text, blah, blah, blah. So let me run it and see what are the results. So 350, let me do a 450 million, V2. Let's try. While this thing runs, let me go to the program and say, okay, evaluation loop, we covered that. Oh, yes, we covered that, Paul. A fully parameterized script, yes, we sent that. And we covered naive prompting, we've seen that. And look, it produces 66% accuracy on the 3B model, which is not bad, but it produces a lot of rubbish outputs. Then we saw how with structured output generation, we increased the accuracy from 66 to 81, super. But more importantly, we made sure that every output coming from the model is actually a car maker. It's not random text. So super. We cover structured output generation here. Super. And we check results. Super. And we check also confusion metrics. I don't know if you've trained classifiers before in your life, but confusion metrics are your best friend. Cool. This thing is running. As you can see, one of the challenges that actually left is you can see that it takes a while to start this thing. And most of the time, if you pay attention, was about loading the model. And this is because I did not implement model caching. Every time that I load the model, I download it again from Hugging Face. A smarter approach is in your function, in the in the evaluate function, as we said, there's a volume attached to it. So what you can do is that when you download the model for the first time, you also save it in a volume. So when you run a second iteration of your evaluation, you rerun the evaluation script, you don't need to download the model from Hugging Face, but you just load it from the volume. And this is way, way faster. I haven't implemented that because I was building it quickly, but this is an obvious improvement that accelerates your development process. And this is very important. When you're doing this kind of experiments, these optimizations really, at the end of the day, allow you to perform, to try many more experiments, runs. So you iterate faster. That's it. Look at this, accuracy 58%. Okay, so look at this. The model, the 3 billion model, 81%, the 450, 58%. Let me check the matrix to see what it looks like. So the matrix is, here it is. As you can see, it's not a bad matrix, like it does not produce garbage because we're using structural, but there are way more elements of the main diagonal which are non-zero, meaning wrong predictions. These results are not very surprising. The 450 million parameter model has less capacity to learn car maker brands. At the end of the day, it has during its training, probably has seen less images of cars and has less capacity to remember that. The 3B is out of the box better. It's not surprising, but you need to perform this kind of analysis because this out of the box performance indicates, okay, your starting point. For example, if you fine tune the 3B, you're going to start already from a strong performance. If you start fine tuning the 450, it's like 58%. It's not that bad, but still far away from 99%. So you will need to spend more time, more compute, and probably larger data sets to manage to fine tune the 450 to perform as well as the fine tuned 3B. But as I said before, choosing one versus the other is both a matter of accuracy, yes, but also deployment constraints. If you're building an app, if you're trying to deploy this thing on self-driving cars, which have less memory capacity, and the 3B does not fit there, then the 3 billion model is not an option for you. You need to go for the 450. And you need to spend more time with the fine-tuning and increasing the size of the data set. So there's always this trade-off. Okay, so what did we do? We did a couple of experiments, and at the end of the day, we saw that the 3 billion parameter model out of the box gives us 81% accuracy. And as I said, this is super nice. I'm not going to lie to you, but it's not perfect. And this is when we ask ourselves the question, what can we do next? And this is obvious. We need to fine tune. Okay. Now, what is fine tuning? Fine tuning is essentially modifying a subset of parameters from the original model to increase the model performance. It's about customizing it to be better at a particular task. Now, fine-tuning is not something new. Fine-tuning is quite old. Like people were fine-tuning convolutional neural networks 10 years ago to increase performance. What has changed in the last 2 years? Model size. Okay, so now models are so large that traditional fine-tuning strategies, which involve taking, for example, the last layers of the network or a subset of layers and fine-tuning them is not good enough. So people, I think it's like 3-4 years ago, discovered more efficient, more parameter efficient techniques to fine-tune models. And the most popular one these days is LoRA, which stands for low rank adaptation, which consists on adding a subset of parameters to your network, reparameterizing some matrices, essentially, using less parameters. This is like it's essentially a mathematical result, which is a matrix decomposition into a product of two, which are smaller ones, which is a good approximation. And this works precisely because the tasks that you need to adjust your model to are usually not that complex. So you don't need the whole space of parameters to change. Only by changing a subset of them, you can solve it. So LoRA is a technique that everyone is using now, is the one I use here, and the one that is implemented inside the fine-tune. Okay, so you go to the fine-tune, this is the second script. Again, you've seen the evaluate, so you will see that this is the local entry point, super, and it has the fine-tune remote function. So the fine-tune is here. And again, it's a modal function. It's going to run on GPUs, of course. And what it does, first of all, we integrate with weights and biases. So we set up the experiment, and this is super important. Now we kick off the job. So you load the data set, you split the data set, you prepare the data set. So you format the inputs and outputs as conversations. This is the format that the language model expects. Now you set the LoRA. So F stands for parameter efficient fine tuning. This is essentially LoRA. So you create the LoRA adapters. And now you set the configuration. So as you can see, there are a lot of parameters, and this is precisely the reason why I extracted configuration in a separate object. So there are a lot of things you need to play with. So it's better to decouple them from the main logic of the code. So this, you can see model parameters, dataset parameters, system prom, LoRA specific hyperparameters, and general training hyperparameters, because fine-tuning is essentially training. So you need to set the learning rate, the number of epochs, the batch size, number of gradient accumulation steps, blah, blah, blah. There are a lot of hyperparameters, okay? So these are passed into this configuration, and this thing defines the trainer, and the trainer starts to what? Start to train. What a surprise, okay? So fine-tuning is a process that takes a while, but I can kick it off so you can see how it works. So for example, if you fine-tune the 3B model, this is the one I did here. So I fine-tune with 6,000 examples, train split ratio 90%, which means 90% of the samples from the train split are for training and 10% are for evaluation. And now the same system prom and user prom that I used before, and now some default parameters. I mean, learning rate 5. I mean, these are standard values. In general, the learning rate, you should not put it too high because it will not converge. It will just go crazy. You don't put it too low because it will not learn enough. Okay, train epochs 15, blah blah blah. At the end of the day, I can kick it off so you see it. So you're gonna go make a fine tune. Make fine tune. Let me see what's the make parameter. So make fine tunes. Okay, so it's actually like this. Fine tune, and then I put what config, and then I can do fine tune. Yes, I can put the fine tune. I put fine tune the 3B model, for example, 3B. But yeah. Okay, this is going to use this configuration here. Now this thing takes a while. I can show you some experiments that I ran these past few days. So we go to weights and biases. Let me go there. Projects. Car maker identification is here. And here it is. So here are some experiments that I was running. Here it is. So now look at this. This experiment is live. This is the one that I just launched. So this it is. Here it is. The weights and biases experiment is live. And this thing is running. And this is why you see this green icon here. Okay. So this thing is running. But in the meantime, let me show you 3 experiments that I ran, I think, yesterday. So I ran fine-tune experiments for 3 different models, the 450 million parameter, the 1.6, and the 3B. Obviously, if you look at this curve, It doesn't. You don't need to be a genius to understand that. Okay, you can clearly see which model is which. This one, so this train loss, which obviously decreases because the train loss always decreases because language models are neural networks. They can fit any kind of pattern, even if it's noise. So the train loss curves, they always go down. Okay, even if your code is completely wrong, they will always go down. But what you can see is that they go down and somehow stabilize at very different levels. This is the level of the 450, this is the 1.6, and this is the 3B. So the 3B is actually dropping pretty fast and it keeps on falling. Okay, not bad, but still, this is not very conclusive. Trade loss is the first thing you should look at, but this is far from being definitive. Okay, if it goes down, super, not a surprise. If one curve goes lower than another, it's better, but still, you need to dig deeper. Why? Because language models, they can fit any pattern in the training data. The question is, do these patterns transfer to the evaluation data set, meaning to samples the model has not seen during training? So the next thing you need to look at in your experiment is the evaluation loss. And let me open here. The evaluation loss here, the curves again rank very similarly for 50, 1.6, and 3. And the good news is that this evaluation curve, so let me just focus on the 3B. Let me do like this. Here it is. This is the 3B model. This curve is falling down. So on the horizontal axis, these are the number of steps of the training step. And you can see this is 0.04, the loss, 0.03, 0.02. So this thing is falling. And as a matter of fact, this thing is continuous falling. So if I had continued the training because I stopped it at 1,000 steps, if I hadn't stopped it, I would probably see this curve falling even more, which, I mean, it's a pity. I should have not stopped this experiment, but you can continue. Okay. But in a nutshell, what this curve falling means is that, hey, the model is actually, the training data is learning some patterns that are not just noise. They transfer to the evaluation data set. So the model is learning, which is great. Okay. So the model is learning, but this is not the whole story. The question is, okay, the model is learning, but how much is it really learning? Because train curve, train losses, evaluation losses are very abstract. These are essentially cross entropy numbers. I mean, what does it mean, a loss of 0.04? It means nothing. What matters to you for you is what's the accuracy of the model. So once you're done, or while you're fine-tuning a model, you need to take the checkpoints and you need to rerun the evaluation to actually understand how good they are. And this is what I'm going to do here. So I think I have a checkpoint. I think I have the 1,000 one here. Here it is. So the last checkpoint. So the model that was generated here. So let me go to the last step here. This one here is the one that is safe in this model volume, and this is the one that I can rerun the evaluation for. So this thing is running. I'm going to stop the fine tuning and let me rerun the evaluation. So let me do leave it clear, evaluate, and the config I'm going to use is this one here. So let me copy this one. Here it is, and yeah, let's rerun. I mean, we're going to be 5 minutes overtime, but it's fine. Let's see. Let's get to the end. We can do it. We can do it if you really want. Okay. I'm sorry, I completely. Okay. I see some questions. Okay, super. I'm going to answer them probably tomorrow because I'm jumping on a plane in 2 hours. But okay, let's see. So, recap. We got a model which, I mean, it's the model that you get at this point. This curve, the evaluation loss falling means, yeah, this model is learning. Now the question is, how much is it really learning in terms of accuracy? And this is what we're gonna find out now. Okay, so this thing starting. Okay. Now loading the model. Okay, still preparing the data. Let me ask a question in the meantime. Is it possible to share any guidance regarding how to create a robust end-to-end data pipeline for fine-tuning multiple versions of Liquid parameters for pre-training and fine-tuning? Someone bothers to answer this question. Thanks. Of course, I bother. Shihab, I bother to answer the question. So, yes, first of all, pre-training and fine-tuning. In general, I don't think you need pre-training. So there are very few companies in the world doing actual pre-training of models. So unless you cannot find a model that was trained on something close to your task, you should not be doing pre-training. So what is pre-training? Pre-training is the first step that any company building LLMs goes through, which is you take enormous amounts of text, raw text, and now you instruct them all to predict the next token in this text. And this is what produces a base model. Pre-training is usually expensive. It takes a while. So what people usually do is they take a base model, pre-trained model, which is more or less has been trained on data similar to what you are trying to solve. And now you do the fine-tuning, right? This is the post-training. So what I'm trying to say here, forget about pre-training, go to the post-training, which means take a specific task, a data set, like, for example, in this case, this one, and apply techniques like LoRA, do exactly what I'm doing here. So post-training. Now, when it comes how you prepare the data, this is specific to your data set. As I said, the two main core principles, like you need accurate and diverse data. You need data that is accurate for your domain and is representative enough of the whole space of inputs your model will see. If you manage to create this data set, fine-tuning is, let's call it, trivial. Now, how do you do that? I did not cover this thing here in this session, but I plan to do in upcoming session. For example, if you're using image data, you can use a tool, which is what I plan to do. We call 51. 51, like GitHub, 51 tool. It's a tool which is specifically designed, as it said here, to refine for building high quality data sets for computer vision. Okay, this is the kind of workflow you need to go through. So you need to analyze, you need to cluster, you need to clean labels, and you need to generate synthetic data for things that are underrepresented on your data set. So you need to get your hands dirty with the data. And this is what answered your question. This is the part, sorry, this is not what I was trying to show. This is the part where you actually build robust data pipelines to generate good enough data sets. Okay. Yes, let me go back to the code. The thing is running. Look at this. It completed, and look at the accuracy. The 3B, the 3 billion model, out of the box at an 81% accuracy. The fine-tuned model, which look really promising. I mean, I'm not gonna lie to you. When I see this curve falling down, I'm like, wow, this thing is learning a lot. Well, this is why you need to check the actual metrics. It has learned, it has improved, but look, only 1% improvement. It's only 82. So if you go and plot the results, let me go to the notebook. Here it is. Let me rerun this thing. You will see that you get the 82% here. And yeah, of the diagonal elements, look at this. What's happening here? Like, again, Audi, it's not perfect anymore. Ford, still a problem. So the model has improved with respect to the base. So the fine-tuning is working, but it's not really, it hasn't taken us our goal. And my goal, as I told you, is like 99% accuracy. So at this point, it's like, what do I do next? Like, I've gone through the fine-tuning, I tried different models. I trained, not long enough because it was still falling, the evaluation loss. I could have extended. What should I do next? And these are the kind of follow-up challenges that I'm going to work on in the following days on my own, and I plan to cover on a future session, and I also encourage you to try. Okay, so the first one, obviously, train longer. The evaluation loss that I'm showing you, go here, was still falling. So look at this, 0.019, 0.005. If we train longer, this curve will fall down. So maybe we're going to boost even more accuracy. Look, the fact that the evaluation loss curve falls, it does not mean that the accuracy goes up. Why? Because what can happen is that what the evaluation loss measures is the difference between the predicted probability and the actual probability. And what happens is that when the model predicts correctly a certain class, and over the fine-tuning, it simply just increases the confidence that this prediction is right. So the predicted probability matches, gets closer and closer to the actual probability, the loss will fall down, will continue falling, because the model is more sure about a correct prediction, which is great. But this does not move accuracy. The accuracy stays the same. And I guess this is what is happening here. The model is learning to be more and more confident about things that the model is already predicting correctly. So the evaluation loss is falling, but the accuracy is not improving. So this is what I think explains the fact that we increase accuracy, but only marginally. So just to make sure that we are not leaving money on the table, train longer, okay? There's no overfitting yet. The evaluation loss curve is falling, train longer. Second thing that I wanted to do to dig deeper, these matrices that I'm plotting here in the notebook after the training, this is okay, but what I would like to do is I would like to integrate them with my experiment weights and biases. How? Every time that I reach 100 steps, so every time that the model reaches 100 steps, I'm performing an evaluation loop. I'm evaluating the model. Apart from that, I would also like to generate a matrix of confusion matrices, because I can track over time. I have a film where I can click next, and I can see how the confusion matrix is changing over time during the training. And this is, for me, more informative than just looking at this curve. Because maybe we can see this phenomena that I just mentioned. Maybe the model is just predicting the same matrix exactly, but it's just being more confident about things that the model is already predicting correctly. I don't know if I explained myself. So improve the visibility of the experiments. Now, if these things are not conclusive, the next thing I would do, I will go back to the data, okay? Something that I skip completely. So first of all, data quality. Are there problems in some labels? Maybe. I don't think it's going to be a big problem, because these are quite popular data set. I guess it has been created. But maybe we have problems of classes which are very underrepresented. So for example, if you look at this matrix, I don't know, look at this. In this matrix, for example, what I see a problem, Ford. There are 4 samples which are Ford, which are misclassified as Volkswagen. So the model is having a hard time distinguishing Ford from Volkswagen. Well, this maybe tells me how many Volkswagen cars are there. Maybe it makes sense to provide more examples. Maybe the model is to understand better the difference between Volkswagen and other cars. So this gives me a hint of, okay, maybe this is something I can try. So data augmentation. This is something I'm going to cover in the future, but this is a hint. What else? Other things are just speed improvements, batching, model caching, process. I mentioned them. They're not really moving the accuracy, but they're going to help us experiment faster. And logging. So these are basically improvements, challenges that I'm going to list to you. Everything is committed. So I saw the question here in the chat, right phone. So everything, I'm going to place the link. Everything is going to be committed, so you can run yourself. And here's the final question. So let me approach this. Let me answer this question, and then we can call it a day. So can I apply a similar workflow and rationale you showed to humanities data? For example, to find keywords in a medieval text and classify their types, or into segmentation for validation tasks? Yes. How would I go about building a structured data set for that? I mean, you need to look. So how would you build a data set? My advice is that you find a similar data set, a similar task, and see how people do it. We can think about that, okay? At the end is basically a text in, text out kind of task. It's not about images, I guess. Or yes, I mean, maybe it's images. But yeah, generating the data set is the most time-consuming part. So generating the data set, filtering and augmenting the data set, this is the part where it's harder to automate. It's the part that requires more like human in the loop. This is the part that, yes, it takes more time. And this is one of the reasons why people, I mean, we're all lazy, but we tend to be lazy at fine-tuning because I need a good data set to fine-tune. Yes, this is the price you need to pay, but in return, you get super small, efficient, fast models for the task you care about. So, I mean, we can continue this conversation. I'm going to share some thoughts later, Luby, about this. But thanks a lot for the question. Okay, so that's it for today. As I said, the code is going to be in the cookbook repository. So here it is. And let me stop this because we are over time. Here it is. Let me stop the sharing. Where it is? Share. Okay. I don't know if I stop the sharing. It's fine. Guys, the recording is going to be also available. So I'm going to, if you want to watch again, I'm going to paste the link tomorrow. And yes, I mean, I hope you learned something new. As I said, we're gonna continue evolving this thing. Okay. My intention here is not to say, hey, I know everything in the world and I'm going to show you the perfect thing. No, I'm more interested in showing you the process. Okay. So the tips and tricks, things that work, things that I tried, and learnings. Because, as I said, it takes some time, love, and care to produce good fine tunes. So let's get there step by step. And yes, I'm going to see what we're going to cover next. But my intuition is we should do a better job at this task. Okay. So far, we got an 82% accuracy on this task, and I want us to go above 90 at least. Okay, so let's see what's the next step. Maybe some data engineering, maybe training longer, but let's put that in as our next goal. Let's increase, let's go above 90, and let's be proud of the model we fine-tune, okay? So that's it for today, guys. I hope you learned something new, and see you very soon. And we are on Discord, okay?